Just to recall, if you can recall, last week we started related to torsion. So those students, they have taken last week lecture. So it was all related to answer. Okay. Talk about this topic in today's lecture. Okay. So after we have related to this torsion, then we will go for solving numerical problem. Okay. Related to this topic, and then we will go for a new topic of today's lecture. So in this part of lecture, the first part of lecture, again, this will be something good. From the very beginning, every student should know what is something he or she get from today's lecture. Okay, you should be able to know what is the normal stress which will be associated with a maximum torsional shear stress. You remember last week when we were talking about torsional load, then we mentioned that whenever load is torsional load, then because of torsional load, the stress which is produced is shear stress. Formula for shear stress and formula for shear strain in last week lecture. Today, we want to know that whenever it is shear stress or maximum shear stress because of torsional load, so what is normal stress which is associated with maximum stress? We would like to know expression for normal stress. Second, you can see failure modes. So again, you remember we have mentioned about types of material. You remember it was a stress strain diagram, okay, where we were discussing types of material. And in types of material, you remember two types are discussed. One is called brittle material and the other is called ductile material. So here, something good you would like to know that when torsional load is applied to brittle material, so what is the failure mode? Okay, to tactile material, so what is the failure mode? So that in real life, you can distinguish between the ductile material and the what is called brittle material because of torsional load. Then, third, you can see there is something with respect to angle of twist. So the angle of twist we have discussed last week. You remember, okay? So, but in this part of lecture, we would like to derive an expression for this angle of twist. So here, remember, angle of twist you can call angular deformation. Like in previous lectures, when the load was axial load, let's say normal load, okay? Then normal load can cause axial elongation, okay? The length may increase, the length may decrease, okay? And because length increase or because of length decrease, okay, there is elongation, and that elongation is called axial elongation, okay? But in this case, it is angular deformation. Because the type of load, remember, it is torsional load. And when by torsional load, then it is bringing angular deformation, okay? So what is the relation or formula for this angle of twist? So that sometime when you need to calculate the value of this angular deformation, then the formula could help you. Next, you can see about power transmission. So again, it will be something required from you people, you students, that whenever you want to now or you want to calculate or you want to find out a shaft can transmit. So there is a formula we will discuss, okay? So the formula will help you to calculate or find out the power transmission by a shaft. Because remember, when we apply torsional load to shaft, so because of torsional load, shaft are rotating. And when shaft are rotating, so the intended function of a shaft is power transmission. So shaft is transmitting power from one point to another. So how much power a shaft can transmit? So for there is a simple formula we will talk about. Okay, mention that we will look into solving some numerical, okay, which will be related to all these things we are discussing in today's lecture, and those things we will discuss in previous lecture. That was regarding shear stress, which is produced because of torsional load. And shear strain because of torsional load. So this is the overview, just to bring to your good notice what was covered. So although the topic is the same, topic is not new, same topic, which is torsional load. Okay. Last week, initially, okay, what we discussed, some definition, some introduction, some nomenclature, and we have discussed for torsional load. Okay. And then what we have done, we have discussed about the angle of twist. Okay, when a shaft is subjected to equal and opposite torques T and T1. And then you remember we have derived a relation for strain in a shaft when the shaft is subjected to you can say torques or you can say torsional load. And then you remember we have discussed about stress which is produced because of torsional load when applied to a shaft. So that is something the overview of last week lecture. Now here what we want to understand, what is the objective. What particular slide you can see. So on the top it is written normal stress. Although you can see in the figure there is a torque. Okay, so there is a circular body which is a shaft, and you can see the shaft is subjected to torsional load, equal and opposite torsional load on the right side and left side. Okay, direction wise you can see they are opposite. Because of this torque, in last lecture we have discussed a shear stress is produced. Okay, and if you look at the bottom figure, so you will remember this is the relation or formula we have derived. Okay, we can see tau, which is a symbol for shear stress. So tau maximum equal to capital T multiplied with small c divided by j. What is capital T? You can see the torque applied to the shaft. What is small c? So small c is a symbol which is used for radius of the shaft. Okay, radius of the shaft. And what is j? J is polar moment of inertia. So this is already we have discussed in previous lecture. In today's lecture, we want to know that when torque is applied to shaft, then what is the normal stress? What is the normal stress? Okay. Now in the top figure you look into, so you can see A and B. A and B, A and B are both differential elements of the same shaft, which is subjected to the same torque. The difference between B is, so A and B are the orientation. If you look into A, so it has got this vertical face, okay, vertical face which is perpendicular to shaft axis. If you draw the shaft axis, so you can find the vertical faces are perpendicular to shaft. What is B? So if you give rotation, if you rotate this differential element A at certain angle, so it will occupy this position. Okay, so this is orientation at some angle. Okay, this is orientation at some angle of the same differential element which is shown in A. Okay, so what is happening when you are changing orientation from A to B? So that is already shown, okay, by the stresses. So if you look into A, so in A there are on the vertical faces and on the horizontal faces shear stress is acting. There is no normal stress. This case, what you can see in A, it is called pure. Why pure? If you remember, like in the case of pure bending, discussed a few weeks before, pure bending was a case where there was only normal stress. There was no shear stress. Okay. This case, you can see it is called pure shear stress. Why? Because you can see on the faces in only shear stress. There is no normal stress. But when you change the orientation, then in B you can see, okay, there are the shear stresses which are shown by these arrows, okay, which are parallel to the faces. And also you can see there are arrows which are showing normal stress. Why normal? Because these arrows you can see they are perpendicular to the. For analysis, you remember what we do. We want to cut the element by a cutting plane. Okay. Now look at A. This is the differential element, and this we want to cut by a cutting plane. And the cutting plane we want to pass along diagonal at 45 degrees. So the orientation, look at the cursor, okay. So the orientation of the cutter, the orientation of the cutting plane is at 45 degree. At 45 degree, okay. When I cut it, when I section it, so I will get two parts. So let me consider the lower part, okay. Consider the lower. So it will be like a can see here, this is the lower half of the differential after it is section. So you can see this diagonal of the triangle. This is basically the cutting plane. Section, because we have cut diagonally. So this diagonal is basically the cross section, and you can see on the cross section there is the resistive force. So this force, this is basically a resistive force. Why resistive force? Because it is acting on the cross section. And if you look into the force, so everyone could see the force is acting perpendicular. The force is acting normal to the plane. Normal to the plane, then for sure it will give us normal stress. Okay, normal stress we represent by sigma. Already we have discussed, okay, in many classes and in many tutorial. But this normal stress we are interested at 45 degree. You can see. So therefore we write sigma 45 degree. Normal force, which is this force, you can see acting on the diagonal plane, divided by area. A is here, area of this diagonal plane. Plane, and what is the area of the horizontal plane? So we assume A naught. So A naught, you can see basically is a symbol which is basically showing the area of the horizontal as well as area of the vertical. So in terms of A naught, area of the diagonal plane will be A naught under root 2. Here you can see force, and force equal to again stress into area. So term x into A naught under root 2. And you can see both are cancelled out. Okay. And you can see sigma 45 degree equal to term x. So basically, you remember in every class what we are discussing, this procedure that we section, and after sectioning, we take one part for consideration. And after we have considered a part of interest, okay, then what we do, we draw a free body diagram. So this you can call a free body diagram, which in every class is our discussion. Okay. If you look into every class or tutorial, so our main discussion, our main focus is upon free body diagram. So free body diagram means just to draw that part in isolation and show all the forces. You can see this is the force which is acting on the part. On horizontal, you can see. So basically on horizontal, if you look from here, okay, so it is what? Shear stress. So shear stress, which is star, you multiplied with stress into area, it will give you shear force. So this is the force on the horizontal. Okay, vertical, again you can see here is star max. Okay, tie is not visible, so it is star max, which is shear stress multiplied with A naught. So with stress, so you know it is force. So this is force on the vertical, horizontal, and this is force on the inclined plane, oblique plane. Okay, so this is basically the free body diagram. And from this free body diagram, then okay, we can see this, which is at 45 degree, is equal to term x. The term x relation, it was T into C divided by J. It is sigma, and this sigma is at 45 degree. The condition is at 45 degree. So at 45 degree, sigma also equal to the same value, which is T into C divided by J. It could be plus and minus. Okay, you can see here in this part C. Okay, we have shown maximum normal stress, which is at 45 degree. So we can see it is on this plane tensile. Consider plus sign, so the plus sign will give you tensile stress. We can see, okay, on these places you can see the stress which is normal, but it is compressed. Consider minus sign, so it will show you this compressive. How you can calculate the normal stress which will be produced in a shaft when the shaft is subjected to the action of torsional load. Okay, about failure mode, but already I mentioned that basically you have studied, okay, two types. One we have called ductile material, and the other we have called brittle material. And you remember we have discussed, okay, what is the characteristics of ductile material and brittle material, etc., etc. Okay, so in detail we have discussed. So here the only aim from this slide or purpose is ductile material or brittle material, they are subjected to torque, and because of applied torque, failure occurs, okay, of the ductile material, and failure occurs of the brittle material. So how can we distinguish, okay, what will be the condition of the surface, okay, the cross section of failure after failure? So you can see here, okay, so in this middle part, okay, this one, the middle figure you can see, so this is ductile material. This is ductile material, and this ductile material is subjected to torsional load. Become maximum, so for sure at maximum load, failure happens. We have studied, okay? Failure happens. So this is the failure of the ductile material because of torsion. So you can see, okay, the surface of the material. So you can see this is a perpendicular. This is perpendicular to the axis of the shaft. If you draw axis of the shaft, so you can see this surface, okay, perpendicular. Okay, so you can say when subjected to torsional load, a ductile material will break along a plane of maximum shear. A plane of maximum shear. That is a plane perpendicular to the shaft axis. So there will be a plane, and that plane will be perpendicular to shaft axis. And in that plane, there will be maximum shear stress. And because of maximum shear stress, this ductile material is failing. Okay. If you look into the brittle material at the bottom, so it is a material, but it is brittle one. When it is subjected to action of torque, and because of maximum torque, when failure happens, then you can see the failure. So you can just again draw, you can draw axis, but in this case, this after failure is not perpendicular. Okay, so you can see. So what will be the condition? You can read from here. When subjected to torsional load, a brittle material will fail along plane perpendicular to direction in which tension is maximum. In this case, when shear stress is maximum, when tension is maximum, you can say sigma tensile normal stress will maximum, and normal stress is acting in what plane? Just on the previous slide we have seen, okay, that is along surfaces at 45 degree, because we have seen in the previous slide that basically whether it is tensile or compressive, so it will be acting, it will be happening at 45 degree. Okay, so in this case you can say that basically along the surfaces at 45 degree to the shaft axis. When ductile material, so ductile material when subjected to torsion, shear stress is the stress which is causing failure of ductile material. But material and subjected to torsional load, then maximum normal stress is the stress which is causing the failure. And onward, inshallah, in your next part of the semester, then there are some theories, okay, theorems of failure. Okay, so in that you will learn, okay, that basically maximum shear stress theory is a theory which is used for failure prediction in ductile material. Maximum shear stress because the failure is occurring because of maximum shear stress theory. And for brittle material, then there is a theory which is called maximum normal stress theory. Okay. Okay. So these are theorems you will learn inshallah in coming part second of this course. Here you can see what is the purpose, what is the aim of this slide. So these are things we have seen in previous lecture. Okay, this is the shaft like an cantilever beam. Okay, and this is subjected to the action of torque. And if you remember, we have discussed, okay, this angle. So this angle you can see this is one line, this is another line, radial line. So in between the two lines, after the torque is applied and this point A has gone to a new position, A bar. Okay, then this is the angle. So this angle is called angle of twist. Call it angular deformation. Angular deformation. Why angular deformation? Because the applied load is torsional load, and you can see this load is basically causing rotation of the shaft. That's why the deformation will be angular or rotational deformation. So here the only thing we want to know, the discussion for this angle already we have made, okay, in previous lecture. Here the only purpose is to get a relation, to get a formula that will help us in calculating the magnitude or value of this angle. Out this relation or formula, then if you recall in the previous lecture, it was the first formula we derived, okay, and this was for maximum produced in the shaft. So you can see it is shown here, maximum, gamma maximum. So it is a symbol which is used for maximum shear strength, and this is equal to C. What is C? So again you can see from the figure, it is the radius of the shaft, and this is the angle, okay, divided by L. What is L? So you can see it is length of the shaft. So this is the relation we have derived, we have seen in previous lecture. Knows a Hooke's law, okay, which is a very familiar law. And in many lectures, okay, we have discussed this law. It is applicable, okay, within elastic range. So from here you can see stress equal to strain times gamma, or you can say gamma, which is strain, equal to stress divided by G. What is G? For time maximum, what is this? So for time maximum, let me take you again. For time maximum, already this is the relation at the bottom. You can see we have derived, okay, in last lecture, which is T multiplied by C divided by J. We want to put this value of term x. So for term x, we put its value, which is T multiplied by C divided by J. And the material property G, we write as it is, okay. The expression we are getting. And this is also giving us gamma maximum, which is maximum shear strength. Now equating the two equation, okay, because both are giving us maximum shear strength. So equating the two, we can get this relation. So what is this relation? This is the relation which gives us angle of twist, which gives us produced in the shaft when the shaft is subjected to the action of torque. What is T? You can see it is a symbol for torque. It is a symbol for torsional load. What is L? Length of the shaft, moment of inertia. What is the modulus of rigidity, which is material constant? Okay. This formula is applicable in the condition when the shaft is having uniform cross section, uniform dia throughout its length. You can see in the top figure. Okay. Shaft is having different dia at different cross section at different points, like in the second figure you can see, okay, it is called a step shaft, okay, because you can see here a step is produced, okay. So here between AC dia is less, and then between E dia is more, and then again at the left between B and E dia is less, okay. So if this is the condition, then what you will do, you will make use of the same formula, but we derived this one but for area, okay, because here dia is changing and for sure length is changing, okay. So when length is changing, so for sure this angle will be changing. Why? Because in the formula L is appearing, okay. Second, here is J. What is J? This is polar moment of inertia. We have said it depends upon the dia, okay. So when dia is changing, so J will be changing, okay. So this formula you will apply section of the given shaft, and then what you will do, you will sum up, okay, the angle, okay, for the whole shaft, and then you will get the overall, okay. Let's say this is angle 1 and then angle 3. So the sum of the three will be angle 1 plus angle 2 plus angle 3. So this is already, if you remember, this equation similar to this equation, okay, not this equation we have studied in previous theory classes. And if you just recall that this one. So here you remember delta equal to F L by AE. So the very famous equation we have got from Hooke's law when the body is subjected to axial load, normal load. So in that case, it is delta, which is linear deformation, okay? And that is equal to F. So it will not be T, it will be F. What will be F? Normal load multiplied with length divided by A, which will be cross-sectional area, multiplied by E. Why E? Because E is the material property when load is normal, okay? And again, you remember, and you can recall that in tutorial we have seen that when the given body is changing in size, okay, from then what we do, we basically use this formula. We sum up for each section the deformation, and then for the whole shaft or for the whole body, we sum up the deformation. Here, basically, we want to know about a formula which can give us the magnitude of the power shaft. So you can see power transmission. Because remember, power equal to two is load and second is velocity. So in this case, what is load? Torsional load. And when you apply torsional load to the shaft, so you can see the shaft is rotating, okay. So what is omega? Omega is the angular velocity of the shaft multiplied with velocity, with angular velocity. This is the simple formula which will give you the power capacity shaft. And what will be the unit of T? It is a torque. So everybody should know the unit of torque is Newton meter. What is angular velocity? So here omega, or you can say not omega, maybe omega, you can say small w. So it will be in radians per second. So angular velocity here it will be in radians per second. Okay, in the given data when it is given in radians per second, then you can use this formula. Okay, and it will be given not in radians per second. It will be given in second. You can say revolutions per second. Okay, we call frequency. Okay, it will be again angular velocity, but the unit will be CPS. Okay, so the conversion from omega to F is when you multiply PS, which is cycles per second, represented by F, with 2 pi, so you can get radian per second. Okay, so this will be the formula that will help you. Okay, just to make sure you can hear me. Can you hear me properly?
Yes, sir.
Students?
Yes, sir.
Okay. And to go for solving numerical related to this topic. From the very beginning, please, every student to be very much attentive, because one topic, okay, only one topic we are discussing now for problem solution. The topic is torsional load applied to shaft. So for sure, the same formula will be applicable in all the numerical 9, 10, 11, whatever we want to solve. Okay. Tutorial, I'm telling you that basically sometime data will be given. Let's say in this case, you can see this is the formula. Okay. Sometime a shear stress will be required. Other data will be given. Sometime the other data will be given. Sometime radius will be required. The other type of data will be given. So basically, it is just to understand the basics, okay, of each topic, and to understand the required formula, okay, and then to understand each and every quantity or term which is appearing, every symbol which is appearing in the formula, okay. Then the rest is very simple. You can see in this case we start from this numerical. So what is required? Determine the maximum torque that can be obtained, that can be applied to a hollow circular shaft of 100 outside dia and 80 mm inside dia without exceeding a shear stress of 60 megapascal or an angle of twist of this. Okay. G is given. Why G is given? Because it is material property. Okay. So it is already given in the table. So from table it is already provided in the data. Torque is required. What is required? Torque is required. And for torque, you have two formula. Two formula. One is this formula. You can see. And this torque, okay, the capital T is basically for torque. And this torque is based on shear stress, because you can see on the left side, time maximum. So time maximum is given how much? 60. You can apply, you can use to find out torque. Also, there is another formula, okay, just we have studied, okay, and that is called angle of twist. I'm taking from different books, okay. So here the symbol for angle of twist is theta. Angle of twist, which is equal to TL by JG. So again, you can see here is what? T. So this T you can calculate using this formula, for which you remember you can use this angle of twist, which is given 0.5 degree. Okay. So this will be the torque based on. So you need to calculate torque based on given shear stress, and you want to calculate torque based on given angle of twist, which is 0.5 degree. Okay. Two values, what you are getting, you will compare. So here this formula you apply, okay, and then you get torque equal to this much. Here this formula you apply for angle of twist, and you get this value of. When you compare the two values, so in one case it is 900 something, and in the other case it is 4000 something. It is only one shaft, and for that one shaft, okay, best value of torque, it will be the safe value of torque. So this will be the answer, okay. And again, if you remember in previous lecture, I have mentioned that basically the good presentation would be to round out, okay, and then to put in kilonewton meter. So you can write it 4.2 kilonewton meter. So this will be the answer. This will be the value of the torque that will be transmitted by the shaft for the given data. Again, shaft is given 5 meter and 80 megapascal is the shear stress, and angle of twist is given 4 degree. Material property G is given, and two things are required. One is in part A, what is the power when when the angular velocity is 20 hertz. So remember, you might have heard this word from even FSC, Hz when it appears. So it stands for hertz. Okay, means cycles per second. As a note, hertz means CPS. CPS means cycles per second. So it is unit of angular velocity. Okay. Now, okay. So two things. One is shaft dia. So let's talk about shaft dia. So this is the formula for angle of twist. Angle of twist is given. Okay, and then torque is required. Length is given how much? Meter. Okay, 5 meter. So here we multiplied with 1000 to convert meter into mm. Okay, because you can see the answer diameter at the end. Okay, it is given in mm. Okay, and then J. So polar moment of inertia for circular body, it is 32. G value. So G value is given 83. Okay. One thing you remember, here you can see, and then it is multiplied with pi divided by 180 degree. So this is the conversion, because the degree, angle given in degree, you will convert into radian. Where I have written. Okay, you remember this well-known conversion. Okay, pi radians equal to 180 degree. Okay, so this is the conversion from radians to degree, or from degrees to radian. So using this small relation or equation, you can convert angle from degrees into radian, right? So you can see dia is okay. So dia equal to 0.11 power 4, which is given in the terms of dia, because that's still not known. But the good point is we have another formula also, which is this one. Okay, the maximum shear stress formula. So here and from here you can see dia equal to this much mm. So this is the answer for dia. For power, we have just seen power equal to torque multiplied with 2 pi f. So you can put the values and you can see power equal to 5.19 megawatt, because what is what? What is basically the unit of power. So in this case, it is 5.19 megawatt. So this is the power the shaft for the given data can transmit. Okay, next, so more or less same things. Okay, what is now given? What is the minimum dia for solid shaft that will not twist through more than 3 degrees? So angle of twist is given, length is given. Okay, given 12 kilonewton meter. So what is required? One is the minimum dia, in the beginning it is written, and second is what is the maximum shear stress. Two things are required. Okay, now since this is given angle of twist 3 degree, so it simply means you need to use formula of the angle of twist formula, and then again the conversion from degree to radian, and put the value. So here you can see what is 12. So 12 multiplied by 6. Okay, what is 6? 6 is basically, you can see 6 is the length. Okay, so L you will put 6 and you multiplied by Newton. Okay, it is in kilonewton. So 12 into 6 into 1000 kilonewton meter. Okay, and again, okay, because we are bringing into what is called mm. Okay, so you can see this conversion from meter to what is called mm. So dia equal to this much in mm. And then the second part, which is maximum shear stress. Okay, is required. So for sure, you need to use the formula of maximum shear stress. Okay, so torque already given, calculated. You put the torque and the diameter. The only two things which are required in the formula equal to 41.27 megapascal. Okay, next, what is this? Steel shaft, 3 feet is the length which is given. Diameter is 4 inch, 15 kilopound feet. So what is required? You can see the maximum shear stress, number one, and second, the angle of twist. So two things are required: maximum shear stress and angle of twist. So this material property is given 12 mega psi. So here, okay, since what is required, maximum shear is required, shear stress. So for sure you will need to apply shear stress. Okay. You put the value of torque. How much is the value of torque? You can see 15. So you can see 15. You multiply it by 1000. Why 1000? Because it is in kilo. Okay. You multiply it by 1000 and then you multiply by 12. Why multiply by 12? Because a torque is given in kilo pound feet. So we want to change from feet into inches. That's why we multiply with 12. Because you can see the shear stress now appearing in the unit of PSI. What is PSI? Pounds per square inch. Since here inch is appearing, so that's why we have multiplied the feet by 12 to convert into inches. So this is the value of the maximum torque. And then what is next required? The angle of twist. So when angle of twist is required, so for sure you will need to apply for angle of twist. And again, values are given. Torque is given, you can see 12. Length is given, how much? 3 feet. J is given, okay. You can calculate J here, okay, already. 4 by 32 for solid shock, okay. Pi d 4 by 32. G is given already 12 mega psi. You put the value and then initially, remember initially what value you will be getting for theta, that will be in radians. Then you will convert into degrees, okay, by the relation. Pi radian equal to 180 degree. So remember, if in the question angle of twist or theta is required, so your answer should be in degree. Okay, you don't live in radians. So this problem you can look into problems of interest. This is the numerical you can see. So from this figure, a lot of data is given. Okay, if you look to, and this figure just for maximum 2 minutes, you correlate this figure with your maybe tutorial 2 or tutorial 3. Very beginning, maybe tutorial 2, when we were talking about the Hooke's law, when topic was Hooke's law, normal loading, axial loading. This numerical quite similar, okay, to that one. Okay, if you cannot recall the tutorial because many weeks are gone, so just remember the tutorial last week, the 2 weeks before. You can say tutorial or problem solution, and the topic was bending, shear force and bending moment diagram. You just correlate this numerical with that one. So then by the end, you will come to know that basically all the procedure, okay, is the same. It is only the type of load which is changing. Sometimes the body is subjected to axial load, which could be normal load. Sometimes the body is subjected to transverse load, like in the case of shear force, bending moment diagram, like in the case of beams we have seen just a week before we have covered, okay, or 2 weeks before we have covered. And sometimes the load applied is what? Torsional load, like in this case, you can see by this arrow, red color arrow. The rest procedure is 100% the same, okay? So here you can see basically this is a shaft, circular shaft. Has got mounting elements like circular disc, okay? This may be gear, this may be flywheel, okay? You can see circular disc at point A, at point C, at point D. So at each point, whether it is point A or B or C or D, there is load applied because you can see this red color arrow. So it shows torque. Point A, how much torque is applied? 6 kilonewton meter it is given. At point B, how much torque? 14 kilonewton meter it is given. Torque given 26 kilonewton meter. At point D, how much torque? 6 kilonewton meter. So this is given. And for each section, you can see length is given. For AB, 0.9 meter, for BC, 0.7 meter, and for okay. Then what is next? Diameter is also given. So if you look into the data, so in the data it is mentioned that shaft BC, which is the middle portion, you can see BC part, okay, of the shaft, okay, hollow shaft, and it has got dia inner 90 mm and outer 120 mm. And this part AB, you can see AB, CD. These parts of the shaft are solid; they are not hollow. Meter, okay, small d. You can see small d here and small d here. Okay, so they are solid shaft having dia small d. Okay. So, okay, this is also given that basically for AB part, you can see the data AB and CD. This is AB and this is CD, okay? For this part of the shaft, the maximum shear stress is also given. How much? 65 megapascal. Now, this is all the information. This is all the given data provided. So we look into that. Number A, minimum and maximum shearing stress in shaft BC. This hollow shaft. Okay. In this shaft, what is the minimum and the maximum shear stress which is produced? Second part, you can see the required diameter D of shaft A, B, and CD. And CD both have got the same dia, which is represented by small d. So this diameter is required, and for this part, what I mentioned, the maximum shear stress is given how much? 65 megapascal. The procedure, you remember, in just a week before we have called shear force and minimum diagram. And what we were doing? Sectioning. And what was the criteria? Between every two load points, take a section. So this is point A, take a section. And when you take a section, so you remember what we have to do? We consider one part of our interest. And that part, we show the free body diagram. And we apply the equilibrium condition. And we obtain the unknown quantity from the equilibrium condition. That's the same here we are required to do, because it is the procedure. Okay, so no change in procedure. The only change is load is changed from transverse load to torsional load. Again, you can see at point B, at point C, there are loads. Okay, so you can section between BC, somewhere between BC. And again, after you section, so you can consider one part, either left or right. Diagram, and then you apply equilibrium condition, and you can get the unknown quantity of the torque. And then you can see at C there is a load, at point D there is a load, so you can section the shaft. And again, you can consider left side or you can consider this right side. Okay, and then you draw the free body diagram and you apply the equilibrium condition, and then you can get the required quantity of the resistive torque. Okay, so this is how. Now we start from this AB part. Okay, so we section between AB, and let's we consider the left side. So you can see at left side what is there, point A, and there will be the cross section. So this is AB part. So this is the loaded point A, and this is the cross section. And cross section, this is the resistive torque we want to find out. So by default, by common sense, you can say that basically applied load and resistive load, what is the procedure, what is the equilibrium condition, they should be equal in magnitude. Okay, or simply you apply the equilibrium condition, which is sum of all the moments equal to 0. So one is 6, one is TAB. Okay, so this will give you TAB equal to 6 kilonewton meter. Okay, so this is required, torque is required, which is the resistive torque, because this we need, okay, for further calculation. Okay, for CD, okay, since AB and CD, they are having the same dia, they are similar, so we also want to know the torque. Okay, so we just consider CD part. Okay, CD, section the shaft anywhere between C and D, we get two parts. So let us consider the right side part, which is simple, because on the right side there is only one load. What is that load? You can see 6 kilonewton. So this will be the applied load, and there will be a cross section. Okay, and the cross section there will be resistive load. So for sure the resistive load should be equal to the applied load. How much is the applied load? 6 kilonewton meter. So therefore you can also say the torque for CD part is also equal to 6 kilonewton meter from analysis, from cross section, from equilibrium condition, right? Okay, what is left? What is left? So one part is left, which is B and C. So you section the shaft anywhere between BC, consider the left side part. So when we consider the left side part, so you can see at point A 6 kilonewton, at point B there is a load of Newton, and here will be a cross section, and in the cross section there will be the resistive torque. So this is point A with the load, this is point B with the load. So these are applied loads, okay? And this is the cross section, and at the cross section, this is the resistive load. So if you look into without going into calculation type of thing, okay, it is just very much torques. These two should be balanced by this resistive torque. Wise they are different, magnitude wise, torque BC should be equal to sum of these two. So if you sum up 14 and 6, you get 20. And okay, but again, if you want, you can apply, okay, sum of all the moment equal to 0. There are three moments. One is 6 kilonewton meter, one is 14 kilonewton, and one is this quantity which we want to find out. So you can see this equation, which is condition of equilibrium, is giving you the value of the unknown quantity or resistive torque, which is 20 kilonewton meter. Now, what we have done so far is we have sectioned the shaft at various sections, at various points, and for each point or section, we have determined the value of the torque. This value of torque we need in further calculation. Okay. Now, what was part one? Was to find out the maximum and minimum shear stress for the hollow portion of the shaft, which is BC part. Section. So in the radius is given. So radius here is represented by C. So C1 is the outer radius, and in the given data, I have mentioned it is given. Okay. So remember last week I have shown the formula for J. J is polar moment of inertia, which depends upon cross section when radius is given. Okay. So if solid shaft, not hollow, solid, so you will need only one radius. Okay. But since it is hollow, so for sure you need two radius. Okay. Outer and inner. So you put the values and you get the value of J this much. We want to calculate maximum torque. So here maximum torque, you can see this is the shear stress distribution, okay, along cross section of the hollow shaft. And you remember last lecture when we were discussing about the shear stress distribution, then we have mentioned that it is varying along this radial length, okay. Or it's zero, so shear stress is zero, you can see. But when you move from zero toward the okay, so stress is increasing. At inner surface, you can see this much is the stress, tau 1. So this will be minimum stress, okay. And then when you go to the outer surface, since radial length or radius is more, so for sure because of more radius, you can see stress will be more, okay. So this you will call maximum shear stress. So here tau 2 is maximum shear stress, tau 1 is minimum shear stress, okay. So tau 2 equal to, what is the formula? T C divided by J, TC by J. Remember, TC by J. What is the torque? But we here write TBC. Why BC? Because this part is belonging to BC part of the shaft, okay? BC shaft. Therefore, we put BC. Why C2? Because we are talking about maximum shear stress. And shear stress will be maximum provided you put outer dia, okay? And what is outer? Sorry, outer radius. And outer radius is C2, okay? Maximum, what is called shear stress, which is 86.2 megapascal. And you can make this relation to minimum by the maximum equal to C1 by C2. C1 by C2 are the radii given. You've already determined. So you can find out the minimum equal to 64.7 megapascal. So this is the answer as part in which the minimum and maximum shear stress is required for BC part of the shaft. Again, I can show you. This is BC part of the shaft in the middle, okay, which is a hollow one, and the radius is given inner 90 and outer 120. Next is required this diameter small d, okay, which is same for AB part and for CD part. And for this part, the shear stress is also given, which is 60 megapascal. Go to this part. This is the free body diagram of shaft AB. Why AB? Because dia of AB is required, okay. And you can see, okay, for shaft AB, okay, the applied torque is 6 kilonewton, the resistive torque is 6 kilonewton. So when we draw free body diagram, in free body diagram, we show all the forces. So these are the forces, okay, applied and resistive. So torque is how much? 6 kilonewton. Now the formula for shear stress, which is torque multiplied by C divided by J, and J is basically something which depends upon. So in this case, the radius is C, okay. So this is the formula for J. T is given how much? 6, you can see from the figure. Is required because we want to find out dia. Okay, so once we find out radius, you multiply radius with 2, you will get the dia. So you put the value and you can see you can get C equal to this much, and then you multiply the C with 2, you get the dia. Okay, so this is the diameter of the AB part of the shaft, okay, for which the shear stress is given how much? To make sure You can hear me, students, huh?
Yes, sir.
Okay,
Yes, sir.
right. But I have mentioned you if there is some question, okay, because when I look into the messaging, chatting, okay. So 11, if there is some question, you can ask me. If there is something, you can ask me, okay. As I have mentioned, don't put in chat, okay, if something for me, question, some comment, okay, because it's not time, okay, that I should look into that. And again, I have mentioned in between you, again, no chatting allowed, okay, because you can chat among you via your WhatsApp group. There is some comment, so the best is you just talk to me, okay, instead of putting a comment. Like for example, you cannot hear me, or sound is less, or there is some net problem, anything. Such thing, everything okay?
So I have a question in the first problem.
Okay.
So regarding the final answer,
Yeah.
we chose the smaller value for the torsional stress. However, in the question, they ask for the largest.
Okay. Let me take you to the slide. Okay. Which slide can you show me? Can you tell me this one?
Stress, first numerical.
First numerical.
Yes, sir. First numerical.
First numerical. Let me. The one. So they say, okay, what is your question? You repeat again.
My question is that they're asking for the maximum torque, and we chose the smaller torque in the final
Yeah,
answer.
good. This is a good question, but because, yeah, but maximum safe torque, okay? Because look, it is the same shaft, okay? One shaft. So for one shaft, we have got two value. You can see on the left side, it is 6,000, roughly you can say 7,000, okay? One value is 7,000, and another value is 4,100, okay. So what is T? Basically T is load, okay. Like you take example of something, okay. So let's say I want your example, okay. I want to take your example, okay. So you are the person, and okay, with some aspect I calculate, okay, and I think you can take this much load, okay. And with some other angle I want to calculate, okay, with some other aspect, and I consider, okay, you can take this much load, maximum load. So this is maximum load you can take, okay. 100, this is maximum load, but this maximum load is based on angle of twist. This is for sure maximum torque, but this is based on angle of twist, because this is the formula we have used, okay. Here on the left side, this is also maximum torque, okay. But this maximum torque is based on another thing. What is that? That is the maximum shear stress, okay. Shaft, and on one shaft, what torque, what maximum load we can apply. So for sure this much load, because much load, so this much load is okay with respect to maximum shear, okay. Because of maximum shear will not happen, but it is not okay because it is exceeding this value, which is given by this angle of twist. So angle of twist could be maximum, okay. How much? So because of this angle, this is the maximum torque the shaft can transmit. So that's why you will decide the lower value, okay. You will define the lower value, because for the lower value, it will be safe both in maximum shear, make, and both in what is called angle of twist, okay. But if you decide the higher value, it is okay. It is safe in Tamex, but it is not with respect to angular deformation. So that's why. And you remember in previous lecture also we have done the same. That whenever, for example, there was uh, comparison between the two quantities, load, okay, etc., the lower value, okay. So for sure both are maximum. When we use the word maximum, here I compare one and these two, and then I say this is the maximum. No, by definition, both are maximum. One is maximum with respect to stress, and one is maximum with respect to angle of twist. So, but between the two, when I compare, then for sure I should go for the value which is safe. I hope you got my point.
Yes, I got your point. Thank you.
So here, and again, if you look into like a cantilever beam, the left side, fixed right side, load, what is the load? Torque T. Okay, and you can see it is a hollow shaft, length is given, and inner and outer die are given. So what is required apart from this information? So okay, uh, the shear stress is given not to exceed 120 megapascal. This is another information given. Okay, already shown here. Okay. Number one, you can see part A. What is the largest torque, or you can say the maximum torque that can be applied to the shaft if the shearing stress is not to exceed this much. So meaning, like it is something covered in the previous problem, we want to calculate torque which will be based on shear stress 120. Okay. Second, what is the corresponding minimum value of the shearing stress? So, okay, this is the shaft given with the given data, and now we want to calculate the value of formula. Okay, you can see tau maximum, you can see, will be equal to Tc divided by J. So it is J. So Tc divided by J will give you tau max. Since we need torque, we write the formula this way. Now we need J. Hollow shaft, it depends upon inner and outer radius. You put the value and you will get this value for the polar moment of inertia. The value for shear stress, which is given 120 megapascal, C is given 0.03. I have written as a note that basically, since we have got two C, one is C1 and one is C2 here, okay? So you will put C2. Here this C will be C2. Why C2? Because C2 is the outer radius, and at outer radius, tie is maximum. Since we are talking about tie maximum, therefore C should be C2, okay? So that's why it is 0.03, or you can say 30 mm, right? So this is the value which is 4.08 kilonewton meter for the torque. Next is tau minimum. So again, this is the relation we have used. Okay, tau minimum divided by tau maximum equal to C1 by C2. What is C1 and C2? They are the inner and outer radii. Okay, and you can say tau minimum is occurring at inner radius. Okay, and tau maximum is occurring at outer radius. Okay, so this is the relation. And then inner outer radii are given. Shear stress is given, so you can get a minimum shear stress for the shaft, which is 80 megapascal in this case. Okay, same problem, same shaft you see, nothing changed, it's same shaft. But what is required here, and for sure, same topic, same formula, whether shear stress or angle of twist, but little change in the data should be applied to the end of the shaft, previous problem, to produce a angle of twist of 2 degrees. In this case, the torque you can see, which is equal to 4.08 kilonewton meter, we calculate it based on shear stress. Okay, so if we make the criteria, okay, of angle of twist, okay, which is 2 degree. So for 2 degree angle of twist, what is the torque this shaft can transmit? Okay, so already this same formula. Okay, so this is the angle of twist, which is equal to TL divided by GJ. Okay, so you make it like this way because we want to calculate torque. Uh, G is already calculated. Okay, is given because G is given material property. Okay, it is given. Next, L is given 1.5, and this angle, what already I mentioned, it is in a degree, so you will have to convert into radians, okay, while putting in this formula. J already we have calculated, J, because this is the numerical, and you can see from here, there is this value we already calculated. So you put all these values, and then you can get which is equal to 1.8 to 9 kilonewton meter. So this is the torque this shaft can transmit based on angle of twist of 2 degrees. It is already covered, okay, like in one numerical. So this is basically the same shaft, but for the same shaft, we can see the torque is how much? 4.08 kilonewton meter. This 4.08 kilonewton is based on maximum shear stress. Combine the two questions in one question, and I ask you select or choose or decide or find out the the safe value or the maximum value of torque which this shaft can transmit. Then for sure, this is the torque for the same shaft, but this is based on the other is also the torque, but it is the power, but based on angle of twist. But when you compare the value, so this value is less compared to the previous. So for sure, you will say this is the value of torque design the shaft. Okay, interesting numerical. Okay, same logic, same concept. You understand? Okay, pay your attention. You can see in the figure. Okay, it is a shaft. You can see because inner dia is given 4 and outer dia is given 6-inch length is given. Okay, read it. So basically, in the question, it is mentioned that if the shaft, what you can see in the figure, is designed in this way with the inner and outer dia and the length. Okay, and this shaft is used for torque transmission. Torque value which this shaft can transmit. This shaft, what you can see, one thing. Second, in the question they ask that if you replace this hollow shaft by a solid shaft, okay, it is not hollow, and that solid shaft has got the same weight this hollow shaft, then will be the torque T that will be transmitted by. This is second point. Third point, that is the third alternative. Okay, if we look for a hollow shaft, case number one. But in this case, the difference will be the outer dia we want to take 8-inch. Okay, okay, but outer is 8-inch, and this shaft is also with respect to weight the same as the given shaft. Then, which could be transmitted by this shaft. So for each option, for each alternative shaft, we are required to find out the value of torque. Okay, and the value of torque, you remember, what is the formula we know. Okay, so we start from this shaft, which is inner and outer. You can see 4 and 6, and length is 8-inch, and something else may be given. We look into given. You can see here 12 kilo psi. Okay, right. So shear stress, you remember, it is given, and then we proceed. Consider the given shaft. Okay, with the outer and inner, the radius which are given. So this is the J formula already know. So this is the J value, polar moment of inertia. And this is the formula for shear stress. Okay. Since we talk about maximum, so for sure we will put C2. What is C2? Outer radius. And you can see it here 3. Okay. This gives us 408 kilo-pound inch. So this will be the torque which could be transmitted by this shaft. Okay. If we go for the second option, in which shaft, okay, and solid shaft for sure has got only one radius, and let's say that radius we call C3 because C1 and C2 already we have used a symbol. Okay, in this first case. So for second case we put C3 as a symbol for that shaft. Now weight of this shaft, the condition is weight of this shaft is similar or equal to weight of the previous shaft. Here in the book it is direct given, but you can start here. Okay, so weight of shaft A equal to weight of shaft B. This is given. Okay, and so you can say specific weight multiplied with volume. Specific weight multiplied with volume is basically weight. So you can write here specific weight multiplied with volume for shaft A equal to specific weight multiplied by volume for shaft B. Name of the shaft. So specific weight depends upon material. So it will cancel out, and you will get volume for shaft A equal to volume for shaft B. What is volume? So you can say area with length equal to area with length. Area with length we get volume. Then what is the length of this one is the same as the previous one. So length and length will cancel out. So you will be left with area or cross-sectional area of shaft A. Shaft A, which one? The given one, previous one, this one, the shaft A. Cross-sectional area of shaft B. What is shaft B? This second shaft. And already the radii of the previous are given. 3. For this one, radius is C3. This I want to find out. So one equation, one unknown, and you can calculate C3. So once you get the radius, then the same formula for torque makes okay. The value of torque, which is 211 inch. So when you go for this option, for this shaft, which is solid shaft, having this much radius, which is 2.24 inch, okay, then the torque will be 211 kilo pound inch. Okay, now you go to think of the third option, okay, in which the shaft for sure is hollow. Radius is its outer dia is 8 inch instead of 6 inch, like in case number 1. So again, weight wise they are same. So you can see the same relation again. Cross sectional area of shaft A, which was the very first shaft, equal to cross sectional area of shaft C. So now this is shaft C again. And here I say that C4 is the radius of this, and C5 is the inner radius. Okay, outer we represent by C4 and C5. So here inner already given 4 inch. Only changes in outer is given. Outer is because you can see 8 inch. Okay, outer dia. So 8 inch is given. So half will be 4 inch, which will be the radius. So the inner is represented. You can see from the figure. Inner is represented by C. So one equation, one unknown, and you can find out the C5, which is 3.317 inch. And once you get the dia or the radius, then since it is hollow shaft, and you can get the value of J. And once you get the value of J, radius is already there, so you can put in the formula and you can calculate the torque value, which will be in this case 636 pound inch. So now if this is the option, okay, then the torque which could be transmitted by this shaft will be how much? That will be equal to 636 kilo pound inch. Okay, numerical you can see it is same like a cantilever become. You can see on the extreme left side it is fixed, but it is subjected to load. Okay, so it is load. Okay, at point A it is loaded point B. Then it is changing in cross section. Okay, three part has got less dia, which is how much? You can see 30 mm. Okay, and then the next you can see the dia is more, which is 60 mm. Okay, and C, and also for C and D. But the difference between B and C and C and D, what is the difference? So between DC, you can see there is a hole of 44 mm dia which is drilled in the shaft. Okay, there between D and C. In this case, then you can say it is a hollow shaft. Okay, and the hollow shaft has got outer dia 60 mm and inner dia 44 mm. For CD, it is solid shaft. Okay, it is solid shaft, and the dia is how much? 60 mm. A or AB part, it is also solid shaft, and the dia is how much? And the length you can see, length for each part is given 0.6 meter, 0.2 meter, zero point 0.4 meter. Loaded point A is given to 50 Newton meter. Loaded point B is given Newton meter. Material property G value is given 27 gigapascal. So you can see determine the angle of twist at point A. Okay, or you can say end A. So angle of twist, what we already have studied and we have got a relation for, so it is required. Now again the procedure will be, since it is a step shaft, the size is changing, the length is changing. So what you remember, I have mentioned that you will consider, okay, each part separately, and you will apply the formula, and then you will sum up, okay, the angle for all the three parts, and then it will be giving you the angle of twist for the whole shaft. Okay. So basically, if you look into the formula, what is the formula you remember? Multiplied by L divided by J divided by G. What is T? Torque. What is L? Length. J, polar moment of inertia, and G, material constant. So in this formula, you look for what is given, what is not given. So L, which is length for each section, is given. No problem. Material property, it is given. No problem. Two things are left. Torque. So for each section, you will calculate torque, find out torque, okay? And J, polar moment of inertia, because remember polar moment of inertia depends upon cross section, and you see cross section is changing, okay? Somewhere it is the dia is 30 mm, somewhere it is 60 mm, somewhere it is hollow, somewhere it is solid. So you will calculate J for each section, calculate T, and then L and G are given, and that's all. You put in the formula and you can calculate the angle of twist. How to calculate torque? Okay, you start, let's say from here, you take a section between AB. Okay, and once you take a section, so you consider one part, let's say the right side part. Okay, so when you consider the right side part, so what is the applied torque? 250. And what will be the resistive on the cross section? For sure 250. So you can see this is the free body diagram. Okay, and this is at point A, the applied load 250, and in the cross section, this is the resistive torque. Okay, so in this case, torque AB, yeah, T, not torque, sorry, T, which is for torque, for portion AB of the shaft will be 250 Newton meter, which you can get from the equilibrium condition. And then you go for next section. After AB, you go for BC section. Okay, okay, you can cut it, and once you cut it, so let's say you consider the right side part. Okay, point A, there is load at point B. Okay, and here will be a cross section where there will be a resistive load. You can see at point A, load is 250. At point B, load is 2000, and this is the resistive torque. And again, if you look into, so for sure, the resistive torque in direction is from the applied torque direction. And again, if you just look into, you can decide that this torque equal to 2000 plus 250, which will be 2250 Newton meter. Or very simply, you just apply sum of all the moments equal to 0 for this case. So there are three moments. Okay. Torque for this portion equal to 2250 Newton meter. The torque for the last section, which is CT, because if you also take a section here, or you take section here, or here, or here, so for each section, okay, it will be the same torque. So torque for DC is also the same quantity, which is 2250. Now torque you have calculated. After torque is calculated, the next thing is polar moment of inertia. And you remember the AB part is a solid shaft for 30 mm dia, so radius will be 15 mm. Solid shaft with dia 60 mm, so radius will be 30 mm. And the next CD portion, there was a hole, okay, 44 mm dia, so inner radius will be 22, and outer is 30 mm. Okay, and very simple, you just apply the formula for J and you calculate the value of J for each cross section. Okay, so AB, BC, CD. So for AB, BC, and CD, you calculate by the formula the value of J. Apply this formula, you put all the known values, and then you can see this angle equal to, okay. So initially, you can see the formula will give you the angle in terms of radian. So it is 0.403 radian. But your answer is required in degree, okay? So using the conversion factor, you can convert the angle from radian into degree. So the answer is at point A or end A equal to 2.31 degree. Okay, so this was the first part regarding what is called torsional load. Next, we want to start the next part of the lecture, which is with respect to pressure vessel. Okay, so I think better we can take 5 minutes break. Okay, not more, because this topic is only theory. Numerical we will go for next class. Okay, so better we go for 5 minutes break, little to refresh. Okay, and then we will start. Let's say by 9. What will be good time? Let's say at 9:40. Okay, to make it 8 minutes. I have at my laptop. Okay, it is 9:32. So at 9:40, inshallah, we will start this next part. Right?
Yes, sir.
Yes, sir.
Yes, sir.
For in which class you will start with?
Then Torsion or torque was the applied load. Your body will be what? Pressure vessel. This pressure vessel will be subjected to applied load. And because of applied load, like in previous all topics, what happens when there is a body and that body is subjected to load? So the load will produce stress or strain. Okay, you can find out stress if required. You can find out strain when required. So it's same in this case, nothing new. It is for sure quite new, very new. But the fundamental, the theory, the concept, the procedure, the mechanism, the approach, whatever we have discussed from day first till today is applicable as well. The only thing is the solid body, instead of calling it a shaft, a beam, now we call it a container. We call it a vessel. We call it a cylinder, like CNG cylinder. Everybody, everyone out of you, you know CNG cylinder. Okay, so CNG cylinder is a container. It is a cylinder which is containing, which is carrying compressed gas. So gas under high pressure. So that's okay. And then when this container or vessel is subjected to external load, so for sure, whenever there is a load which is acting on the body, will cause stress and strain. So here, like in previous lecture, the purpose, the aim, the objective, the intention is to calculate what are the stresses which will be produced in pressure vessels when these pressure vessels are subjected to the action of external load. Now, a question. From where does the external load is coming? What is something causing load on the pressure vessel? Is or it is the liquid which is under pressure vessel, which is contained within the vessel. So that pressurized fluid is causing the vessel because of the pressure force, because the gas under pressure is exerting pressure on the sides and walls of the vessel. And because of pressure, pressure equal to force by area, a very common formula definition, pressure equal to force by area. So whenever there is pressure, so because of pressure, there is a force, F by A. Okay, F by A is pressure. So this force, which is because of pressure, is called pressure force, which is exerted by the pressurized fluid on the sides or walls will be the load, which we will call action. So it will be the action the gas will be doing on the vessel. It will be the load the gas or the fluid will be exerting on the vessel. Now the vessel, the material of the vessel will react, will oppose the applied load of the fluid. So what will be that load? Like in all previous discussion, in all previous lecture, the load which is coming from within the body as a reaction, as a resistance, is called resistive force, is called internal resistive force. And when all our discussion tutorial from day first till now, till today, even in case of torque, at cross section, we have shown torque, and that was resistive torque. Whenever there is resistive force, internal resistive force, so that is giving what? Stress. What is stress? Stress is due to resistive force. So what is the stress, or what are the stresses which are produced in the pressure vessel? This is the objective. This is the aim. This is the purpose. This is the intention of this topic. Next, this pressure vessel, what you can see on the slide, okay, in that, okay, not in figure, but in words, pressure vessel, they are basically of two types. It is written thin walled. So for sure, by common sense, a question may come to our mind, an idea may come to our mind that for sure there would be, there could be, there should be, there must be thick wall pressure vessel as well. So thick wall pressure vessel for sure are there, but that is part of your next semester. Inshallah, you will study in third semester. So here thin wall, like wall. What is wall? So basically, cylinder or the vessel which is containing gas or fluid or liquid. Okay, that is a container. That is a vessel. So that is called wall thickness. So when wall thickness is very less compared to radius, then that is called thin. When that wall thickness is more, is reasonable, so that will be called. So in today's lecture, we want to look into thin. Next semester, inshallah, with the will of Almighty Allah, we will look into the second part that will be called thick wall pressure vessel. So for sure, for this part of lecture, also it will be something great, something good, something important. Should know, must know what is something he or she is required to understand, to learn from this part of the lecture. So for sure, number one, you can see, you should know the classification, the types, the categorization of the thin wall pressure. And then you should be able to analyze the thin wall pressure for the sake of determination of stresses which will be produced in this vessel as a result of external load acting on this vessel. And you will come to know, then you will be expected to compare the stresses. Is more, which one is less, what is the relation between the stresses which are produced in this pressure vessel. And then, like in previous all cases, whenever we have discussed formula like bend stress formula, like torsional stress formula, so we have mentioned that whenever we are deriving a formula, so we derive formula in light of assumptions. In light of those assumptions, we derive the formula. So here also, since we are going to derive equation or formula, formulation or mathematical model or stresses, so therefore we would like to assumption. So assumption, you should be able to know what are the assumption under which the stresses are derived. And then nothing is perfect. Like in previous lecture, for formulas we have mentioned there are limitations. I have some limitation as a human being. You have got some limitation as a human being. You have some limitation as a student. Okay. So all the time in this world there will be, whether human or product, okay, limitation. Nothing is perfect. Will be there in the paradise. Okay. May Allah succeed us all to get into paradise. So limitation is for sure all the time there. Since we are talking about formula, we are talking about, so what are the limitations? What are the drawbacks which the formula has got, which we want to derive for this case of thin wall pressure vessel? So already I mentioned that pressure vessel, basically they are containers and they are carrying a fluid, maybe liquid, maybe gas under high pressure. Okay. So examples are there: compressed air tanks, okay, water pipes, etc. They could be in the shape of cylinder, they could be in the shape of tanks, okay. And the purpose of this cylinder or vessel is to store fluid under pressure. Okay. Your duty, your aim, your objective, your responsibility as an engineer would be to analyze this structure. By this structure, I mean pressure vessel, okay? So that you could be able to determine the stresses which are produced in the vessel because of the internal pressure, because of the pressure which is exerted by the compressed gas or liquid, which is contained inside the cylinder. So you remember, you should have, or you must have heard, okay, in the TV news, etc., in your surrounding, in real life, the what is called gas cylinder, CNG cylinder, okay, because the coaches, the buses, okay, the cars, the cylinder, and the cylinders are carrying gas under high pressure. So sometimes you remember, okay, when the explosion happens of this cylinder, so how much damage, okay, how much loss to the lives of people, passenger, and to the property, the coach, the car, the bus, they are carrying, they are causing. For this particular reason, that they are causing very big loss, very large, very big loss to both lives. For as a designer, It is your duty, it is your responsibility to design, the time you want to fabricate, the time you want to manufacture these pressure vessels. So utmost care, very much care should be given time, the time of manufacture, the time of fabrication of these vessels. So you can see in the figure, basically we want to talk about the classification of the types. So we, when look into the types or categorization of the thin wall pressure vessel, then there are two types, cylindrical and the other is called spherical. And the terminology, the name, the title to each type is given based on the shape. You can see from the figure. On the left side, it is cylindrical shape, cylindrical pressure. On the right side, it is in the shape, in the form of spherical. So you will call spherical pressure vessel. So these are the two types of the vessel. Assumption. So number one assumption, you can say that basically there are two dimensions for the. One is thickness, small t, and one is radius, or. So since we are talking about thin wall cylinder, then for thin wall cylinder, the thickness is very, very less compared to radius. That's why they are called thin wall pressure vessel. Okay. Another one, the pressure which is small p, which is the pressure exerted by the fluid. Okay, it is assumed to be uniform and everywhere positive. And atmospheric pressure outside. Okay, inside is the gauge pressure positive. Okay, it should be positive, because if it is negative, so that will be vacuum pressure. Okay, so in that case you can think of, if atmospheric pressure is more than the inside pressure, okay, then there will be buckling, there will be bending of the cylinder inward. Okay, so just to avoid that, we assume it is positive inside. It is more than which is outside, which is the atmospheric pressure. Third one, geometry and loading are symmetric. So you remember in the beams when we were discussing, okay, the shear force minimum diagram. So there we are quite familiar with the geometry, or with symmetry. Okay, that and it was something very, very much simple. That time it is symmetrical. You remember, so it was quite simple to calculate the reaction, etc. So here also we assume that the loading is okay, there is symmetry of these vessels, and anything which might affect the symmetry. What is something that may cause to affect? So that could be either the supports, or those could be the end caps. So these things which are causing or which are affecting the symmetry, we ignore, we neglect in the analysis. To talk about the stresses, okay, and when we want to talk about the cylindrical type first, because we have mentioned two types. Okay, one cylindrical and one spherical. So first we want to consider cylindrical, and you can see the figure is cylindrical, and you can see the differential element. Okay, there are two stresses, one is sigma 1, one is sigma 2, and you can see sigma 1 is called hoop stress and sigma 2 is called longitudinal stress. Why longitudinal stress? Because in the figure you look into sigma 2, so sigma 2 is acting along axis. Anything along axis is longitudinal. Axial stress. The other one is hoop stress. You can also call it tangential stress. Why tangential? Because if you look into sigma 1, so since it is cylinder, so you can see this is tangent to the surface of the cylinder. So you can call it tangential stress. You can call it hoop stress. What is the procedure for stress determination? We want to analyze the cylinder for sake of stress. And what is the procedure? We want to section. We want to section by a cutting plane, and we divide the cylinder into two parts. We divide by two parts. Okay, no, remember, in this case, the cutting plane, the cutter you want to pass, so that will be along axis. Okay, along axis of the cylinder, you want to pass the cutter and you want to divide the cylinder into two parts. After you divide into two parts, you consider one part, okay, for analysis. Part you consider, so what you do, what we have seen in the previous lecture, we consider a differential element, okay. So this is basically a differential element of the cylinder we have considered for analysis. So here you can see the length of the differential element we call del x, x-axis, okay. This is the small rectangle you can see, okay. So this is the wall, okay. Here you can see cylinder wall, okay. So it's the cut portion, and you can see R is the inner radius, okay. The symbol small r inner radius, and small t you can see the thickness of the wall. Remember, there are I mentioned in the beginning. One is the force which you can see P multiplied with dA. What is dA? It is area of the differential element, because this we have considered a differential element. So when you multiply area with pressure, what is small p? This is the pressure. You can see the arrow shows, okay, the pressure exerted on the cylinder, the direction of the arrow shows, okay. So this is the pressure which is exerted by the gas on the cylinder, and this pressure multiplied with area will give you pressure force fluid on the cylinder. As a result, there is a resistive force, there is reaction from within the material of the and you can see area you multiplied with sigma 1. So stress multiplied with area is force. So this is force, but this is resistive force. So one is applied force, P into dA, one is resistive force, sigma 1 into dA. Why we call it sigma 1? Because sigma 1 here we have called tangential stress or hoop stress. Because when you see like a tangent to the surface, okay, that's why it is sigma 1, because it is hoop. Forces again, this is the free body diagram, but in every lecture we are discussing. So we have the shown the free body diagram, and we have shown all the forces acting. And what we do, we like in all the discussion previous, we apply equilibrium condition. Sum of all the forces equal to 0. So there are two forces, applied and resistive. And the area you can see, okay, let's say if we talk about this area which is multiplied with sigma, so you can see this is a small rectangle, okay, the wall, this is the wall which is offering resistive force. So multiplied with T thickness, it will be the area of this small rectangle. There is small rectangle, okay, the wall, okay. So del X multiplied with T. So this area plus this area, you can see thickness multiplied with del X. So this is the cross-sectional area. For pressure, you can see it is the area. So how can you calculate the area? You consider this rectangle and having R plus R, 2R, which is the vertical side, multiplied with horizontal side, del X. Multiplied with del X. And you can get sigma 1 equal to PR by T. So this is the relation, this is the equation, this is the formula which is giving us hoop stress. Intensity of pressure exerted by the gas on the surface of the cylinder, radius of the cylinder. What is small t? Thickness. We want to know the other stress to. Now for this again procedure is the same. We will have to section it, and after sectioning we will draw the free body diagram, and once we have drawn the free body diagram, then what we do, we apply the equilibrium condition, sum of all the forces equal to 0, and the equilibrium condition give us something which we need, in this case sigma 2. In this case required is that the cutting plane, now you will pass the axis. You can see the cursor, okay, this is the cutting plane, okay. So I want to cut cylinder, okay, by a cutting plane which is perpendicular to the axis. So when I cut the cylinder into two pieces, let me consider the left side part of the cylinder. The left side part of the cylinder in the figure side, okay. Cross section, the ring you can see, okay. So this is the cross section we have exposed after cutting, okay. There are two forces. You can see, okay, and you can look into the direction of the arrow, which is the force acting on the cylinder. From the wall, you can see, okay, there is a resistive force. Look into the direction, okay. So it is the resistive force, okay, which is acting against the applied force, and this we call sigma 2. And this sigma 2 we have called longitudinal. Why we call it longitudinal? Because if you look into the figure, so the direction of sigma 2 is along cylinder. Therefore, we can call it axial stress or we can call it longitudinal stress. Now, two forces again, and the sum of the two forces equal to 0. So you simplify and you can get sigma 2 equal to pressure multiplied by radius divided by twice of thickness for the longitudinal stress. The two stresses, there are two stresses. Okay, one is this hoop stress PR by T, longitudinal stress PR by 2T. So for sure, you can come across this relation that sigma 1 is twice of sigma 2. So this is the comparison of the two. This is the relationship between the two. That sigma 1, which is more, and sigma 2, it is less. Okay, and sigma 1 is equal to twice of sigma 2. So this we can call a relation between the two stresses which are produced in the cylinder. So these are the two stresses we have determined for the type of cylinder, sorry, for the type of vessel when it is in cylindrical shape, like the one you can see. When the shape is spherical, the slide and the figure, so now it is not a cylinder, it's a spherical. In this case of spherical vessel, which are the longitudinal and the hoop stress, both will be equal to one another. Why? Question, why? Answer, because if I cut this sphere by a cutting plane horizontal, it by a cutting plane vertical, no problem. Same thing, because in this case there is no length, it's only dia. So this is dia along vertical, along horizontal dia. So if I'm cutting vertical, so I'm cutting along dia. If I'm cutting horizontal, along horizontal, so I'm cutting along diameter. In case of cylinder, there are two directions. Length, because it is a cylinder. It is a cylinder. So I can cut it along cylinder. So if you cut it along cylinder and you get two pieces, so those pieces different compared to when you cut it along radius. Okay, this is the radius. So you can cut it along radius. So there are two dimensions. Okay, there are two directions, longitudinal and radial. Okay, so in this case, the reason sigma 1 is different from sigma 2 because there is cutting plane along x and cutting plane along what is called radial. But in this case, okay, so for this particular reason, be equal. Now let's say I cut it vertical. Okay, I cut it vertical. I will get two pieces. Let me consider the left side part. Okay, so this is the free body diagram you can see. So again, like in previous case of cylinder, you can see PDA and the direction you can see. Okay, so it is the pressure force acting on the cylinder. Okay, so this ring is the cross section, and on the cross section there will be shear force. Sorry, there will be a resistive force. Okay, so you can see the direction is opposite to the applied force, and this will be sigma 2 into dA. But you have seen here. Okay, so this one, free body diagram. If you look into this one, they are similar because in this case also, okay, you can see this is the cross section. Okay, the ring, and the ring which is the cross section is giving you by dA, it is the resistive force, and this PDA, it is the applied force. Okay, so same here. Okay, so again, two forces, and sum of the two forces equal to 0, and like in previous case, you will get sigma 2 equal to PR by 2T. We got sigma 2 equal to PR by 2T. Okay, now since sigma 1 and sigma 2 they are both equal, therefore you can say sigma 1 equal to sigma 2 equal to PR by 2T. Now, when it is a spherical vessel, then you will remember that the two stresses another, and in magnitude they are equal to pressure multiplied with radius divided by twice of thickness. So some limitation. So limitation you can see basically the wall thickness should be very small compared to the radius, which is small t, must exceed the external pressure, what already we mentioned. Okay, so that inside pressure is positive, and there is no inward buckling, inward bending. Okay, of the vessel. And again, what is there? Okay, so in this case, remember what we mentioned, that applied external load is because of the pressure P only. Loads we have ignored. Let's say the weight of the pressure vessel, because the pressure vessel has got its weight. There may be reactions. So all these things we have ignored in the analysis. The only thing we have taken into consideration in the stress analysis is the applied load due to the pressure P, which is exerted by the fluid on the vessel. And then the formula what we have derived in this uh, lecture for pressure vessel, they are workable, they are okay, they are valid wall of the, except those points where there will be concentration, stress concentration. Remember, in case of gravitation we have discussed, okay, stress concentration point. So basically these are those points where concentrated load is acting, okay, because it will be the point of application of load. And if you remember, we have mentioned that for sure at point of application of the load, stress would be more because of the load. And when you are moving away from the point of application of load, so stress will be, the effect of stress will be less, the effect of load will be less. Okay. So this is one point. Another point could be for stress concentration. Let me take you to one. Shaft solution we have mentioned, step shaft. Okay, shaft like this one. Okay, so this is called a step shaft. Why step? Because here is dia 1 and then another dia. So here you can say sudden change in cross section. Okay, so this is a step provided. So where there is sudden change in cross section, so at those points there is stress more compared to the other points. Okay, at which there will be the effect of stress concentration. To those points, the formula is not applicable. Question why? Because the stress is more compared to the stress value which will be given by the formula derived. So these are the points. So that's all from any most welcome. Otherwise, you are free to go for other classes. Last point. मेरी आवाज खराब थी अच्छा अल्लाह मेरी आवाज को ठीक करे अल्लाह हम सबको ठीक करे चले जी नो वरी आई विल वेट
की वजह से
अल्लाह हम सब आवाज भी अच्छी हो सेहत भी अच्छी हो सब कुछ अच्छा हो दुआ मांगना तो कोई बुरी बात नहीं ना
आमीन
चले जी यहाँ पे जनाब बात ये चल रही थी प्लस डिराइव किए वो फार्मूला थ्रू आउट वॉल ऑफ द वेसल एप्लीकेबल है पॉइंट्स के जहां पे स्ट्रेस कंसंट्रेशन होगा का जो वर्ण है या टर्मिनोलॉजी है वो खुद बताता है कि भाई वो पॉइंट्स जहां पे स्ट्रेस कंसंट्रेटेड हो मतलब स्ट्रेस ज्यादा हो कौन से पॉइंट्स हैं वो वाले पॉइंट्स हैं जहां पे या तो लोड अप्लाइड हो इट इज द पॉइंट ऑफ एप्लीकेशन ऑफ कंसंट्रेटेड लोड जहां जिस पॉइंट पे लोड होगा तो उस पॉइंट पे लोड का मैक्सिमम इफेक्ट होगा और स्ट्रेस इज बिकॉज ऑफ लोड ठीक है ना तो उस पॉइंट पे जाहिर है स्ट्रेस भी ज्यादा होगा लेकिन जो जो आप उस पॉइंट ऑफ एप्लीकेशन ऑफ लोड से थोड़ा आगे जाएं so then the effect of load will be decreasing and you can say the stress effect will be decreasing. Okay, so this is one thing which can give rise to stress concentration. Another is figure of the step shaft. Okay, अगर आपके पास कोई एक शाफ्ट है जिसमें कोई स्टेप नहीं है इट इज यूनिफॉर्म डाया शाफ्ट ट्रेन का नहीं होगा बट इफ यू प्रोड्यूस अ स्टेप शाफ्ट जिसमें दो पोर्शन हो एक पोर्शन का डाया एक हो और दूसरे पोर्शन का डाया सो फिर जिस तरह मैंने आपको फिगर में बता दिया देयर विल बी अ स्टेप ओके सो दैट इज कॉल्ड सडन चेंज इन क्रॉस सेक्शन बिकॉज फ्रॉम लेस यू चेंज टू मोर डाया और इन अदर वर्ड्स फ्रॉम मोर डाया you change to less dia at some point. So at that point where you are changing from more to less or from less to more dia, it will give you the stress concentration. Meaning at that point stress will be more. कैसे वो फिर इंशाल्लाह बाद में बताऊंगा, बट द ओनली थिंग यू कीप इन माइंड इज दैट इज द पॉइंट एट विच स्ट्रेस विल बी मोर कंपेयर टू which are away from that point. So फार्मूला इसलिए फिर एप्लीकेबल नहीं है कि उन पॉइंट पर जो स्ट्रेस ज्यादा होगा, आप फार्मूला अप्लाई करेंगे तो फार्मूला आपको जो वैल्यू देगा वो उससे कम होगा. So formula are not applicable to those points where there will be effect of stress concentration. Anything else?
सर वो जो assumptions में हमने सिमेट्री की बात की सर, वो जरा अगर दोबारा बताइए, समझ नहीं.
सिमेट्री है ना कि भाई लोड के हवाले से, ज्योमेट्री के हवाले से. फॉर एग्जांपल अगर मैं आपको फिगर की तरफ लेके चलूं, ये आपके पास फिगर है, ठीक है जी. इसमें दो टाइप्स हैं, सिलेंड्रिकल भी. किसी एक की बात करते हैं, लेट से जनाब इसकी बात करते हैं सिलेंड्रिकल की, ठीक है ना. अब सिमेट्री से होनी चाहिए कि फॉर एग्जांपल अगर आप इसको बीच में काटें, बीच में कंसीडर करें या राइट साइड कंसीडर करें, तो ज्योमेट्री ऐसी हो, कंस्ट्रक्शन ऐसी हो, फैब्रिकेशन ऐसी हो कि जनाब आपके पास सिमेट्री हो. ये ना हो कि लेफ्ट वाला पोर्शन, फॉर एग्जांपल आप मिडिल से ले लें लेफ्ट की तरफ, या मिडिल से ले लें राइट की तरफ, कि मतलब क्रॉस सेक्शन में कोई चेंज हो कि भाई ये लेफ्ट वाला सेक्शन या पोर्शन ऑफ सिलेंडर हो, उसका डाया ज्यादा हो या कुछ वाल थिकनेस ज्यादा हो या उस पर कुछ और मतलब पार्ट्स हो, एडिशनल पार्ट्स हो, और राइट वाला अलग हो. नहीं, जब आप इसको सिमेट्री इसकी देखें तो सिमेट्री इसकी बराबर हो. जिस तरह अगर आपको याद होगा हमने बीम में पढ़ा था कि भाई बीम इज सिमेट्रिकल, और वाई तो हम देख रहे थे कि भाई लेफ्ट पे जो रिएक्शन है वही रिएक्शन राइट पे भी है, और लेफ्ट से लोड मिडिल पे है, तो मिडिल पे है तो मतलब मिडिल से लेके लेफ्ट सपोर्ट तक एक ही लेंथ है, वही लेंथ जनाब आपका मिडिल से लेके राइट रिएक्शन की तरफ से है. सो दिस इज कॉल्ड symmetry with respect to load, symmetry with respect to shape.
Yes, thank you.
So anything?
सर ये जे के
Otherwise,
हम लोग यूज कर रहे होते हैं जे के लिए पोलर मोमेंट ऑफ इनर्शिया.
so
तो
polar
इसकी
moment
वैल्यू जी
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 जी सवाल आप कंप्लीट करें, सवाल कंप्लीट करें.
डिफरेंट वैल्यूज हो रही हैं. तो लास्ट लेक्चर में हमने सिर्फ 2 रिलेशंस देखे थे ना पाई बाय 2 के, लेकिन यहाँ कुछ और रिलेशंस भी आ रहे हैं. तो ये हम कहाँ से देख लें फिर?
एक मिनट में लेके जाता हूँ आपको ना. हाँ, बहुत आसान है, इसमें कोई मसला नहीं है. ओके, हो सकता है आपको इससे मे बी हियर. तो यहाँ पे अगर आप देखें ना, यहाँ पे कोई वही फार्मूला है जो मैंने आपको बता दिया. फार्मूला कौन से हैं देखिए, मैं आपको लेके जाऊं. फार्मूला होना चाहिए बिकॉज इट डिपेंड्स अपॉन क्रॉस सेक्शन. ओके, इट डिपेंड्स अपॉन क्रॉस सेक्शन. और अब सिर्फ ज़हन में ये दो चीजें रखें, आपके लिए फिर आसान हो जाएगा. एक न्यूमेरिकल सॉल्व किया जो 3 सेक्शन से ये वाला आई थिंक. हाँ, ये देखें, इसमें अगर आप देखें ए बी पोर्शन और बी सी पोर्शन दोनों क्या है, दोनों जनाब सॉलिड हैं. का डाया ज्यादा है बीसी का बमुकाबला ए बी. देखिए ए बी वाला या बी सी वाला फार्मूला वही है, पाई बाई 2 मल्टीप्लाइड विद रेडियस पावर 4 सी पावर 4. इस तरह बीसी के लिए देखें तो पाई बाई 2 डिवाइड बाई रेडियस पावर 4. फार्मूला क्या है, व्हाट इज सी, व्हाट सी इज रेडियस. ओके, सो व्हेन इट इज, क्योंकि जब भी आपके पास शाफ्ट होगा, शाफ्ट या सॉलिड होगा या हालो होगा. आप ए बी और बी सी दोनों में क्या है, इट इज सॉलिड शाफ्ट. जब सॉलिड शाफ्ट होगा so this is the formula. ए बी पे देखें या बी सी के दे, there is no change in formula. 2 multiplied with radius power 4, pi by 2 multiplied with radius power 4. अच्छा, जब हालो होगा, जिस तरह आप नीचे देखें फिगर में सीडी पोर्शन पे, तो यहाँ पे जनाब आपके पास 2 डाया हैं. तो जाहिर है जिस तरह आप एरिया मालूम करते हैं ना, क्रॉस सेक्शन एरिया आप देखें ना, अब जब आपके पास होगा सॉलिड क्रॉस सेक्शन तो एरिया हम किस तरह मालूम करते हैं, स्क्वायर, पाई और स्क्वायर. लेकिन जब हालो होगा तो फिर अरे क्या होगा, उसमें जनाब आपका इनर आउटर दोनों रेडियस आ जाते हैं. सो सेम आपके पास जो CD सेक्शन आता है चूंकि हालो है तो उसमें क्या होगा, लेकिन अगर आप फार्मूला को देखें तो π/2 4, फार्मूला वही है π/2 रेडियस पावर 4, लेकिन ये आपके पास वो ओवरऑल आ रहा है ना, ओवरऑल देखा C2 क्या है, ये भी रेडियस है, C1 क्या है, ये भी रेडियस है। सो रेडियस से रेडियस निकालें, अगेन आपके पास रेडियस आएगा, but it will be the overall cross section, okay, it is giving you the overall cross section. So these are the two formula, इनके अलावा कोई और फार्मूला नहीं है, ठीक है ना, इनके अलावा और कोई फार्मूला है नहीं। अगर क्लियर है अच्छी बात है, बता दें कहां पे, ताकि हम पर्टिकुलर स्लाइड पे जाएं और वहां से आपको मैं बता सकूं।
ठीक है सर।
जी ओके,
Thank you, sir.
so if no question more, so thank you very much, inshallah coming week, Allah Hafiz.